So we're looking at just practicing some integration by parts. So again, the integration by parts involves a few things. First of all, we need to recognize if the integral is applicable for parts. Okay, so typically it's a multiplying type where you have a couple factors in there. What you have to recognize which part, or you have to decide which part is going to be the u and which part is going to be the dv. And the way we choose that is we typically will choose, the strategy is we choose a dv that includes the most complicated part of this that we are able to integrate. Okay, so once you've chosen the u and v, dv, you need to generate the other parts, the v and du, by integrating the dv to get v, differentiating the u to get the du parts. Okay, and the whole purpose of this is to generate an equivalent expression that has a different integral than what you started with. And hopefully that new integral is one that is easier to work on or anti-differentiate than what you started with. Okay, so that's the whole point of it. And again, this formula really is just a rearrangement formula allowing us to generate a different integral that hopefully we can integrate. Okay, so we look at this, we need to decide, is this a standard integral? Is this one we can do by substitution? Any rearrangements? Okay, none seem to work, so we have to try to apply integration by parts. So here we want to choose a dv that is the most complicated part of this that we are able to integrate, and that would be the sine x dx. Okay, so that would be my dv, and then that would make the x the u. So I'm going to let u equal x. I'm going to let the dv equal sine x dx. So we're going to integrate the dv, we're going to differentiate the u, so du is equal to dx. Okay, the change in u is just going to be the change in x. When we integrate dv, the v becomes negative cosine x. Okay, so those are the parts that I need to generate. So now I'm going to apply the formula. Okay, so I'm going to see if the new integral is going to be something I can use. So it's going to be u times v. So it's going to be u, which is my x. The v is what I integrated, negative cos x. Okay, minus, and this is the part that is key. We want to generate a new integral here, and hopefully that new integral is one that we're able to do. So this becomes negative cosine x, and then the du is just dx. Okay, and so what we've then generated is, when we look at this piece here, we have to evaluate, is this easier than what I started with? Yes. In fact, it's one I can evaluate. So now I can just continue. This integral then is going to be negative x cos x plus the antiderivative of cos is going to be sine, and then we have a plus c. And we can always check these. We can always do a check by differentiating this. So I'm going to just test it. Check to see this is actually going to work. The derivative of that expression, negative x cos x plus sine x plus c, the derivative is going to be, using product rule, negative cos x plus negative x negative sine x plus cosine x. Okay, so that's going to be the product rule part. The cos x's cancel out. I end up with x sine x. Yeah, that's exactly what I started with. So this is the correct antiderivative for that expression. Okay, so we can move on to this next one. So when we choose the parts, again, we want to choose the dv parts where the dv is going to be the hardest part of this that I can integrate. And that's going to be the most complicated part there. So we're going to use that as our dv. And that makes x our u. Differentiate. So I'm going to differentiate du to get dx. And I'm going to integrate dv to get e to the x. And there's my parts that I need. So I'm going to fill in my parts. It's going to be x e to the x minus the new integral is going to be e to the x dx. And again, this one works out quite easily because of the e to the x. Okay, and again, we don't need to check all of these, but for now, since this is new, we're going to check some of these to make sure that we are in fact doing this correctly. And secondly, to just verify this actually does work. So I'm going to differentiate my integral here. Okay, so as I differentiate this, I'm going to use a product rule, e to the x plus x e to the x minus e to the x, okay, plus 0. So there's the square brackets is my product rule. Those e to the x's cancel out. I'm left with x e to the x. That's the correct integral. Okay, so here's another one. We did ones like this before. We had log x over x, where the derivative of this was substitution, because log x, the derivative, would have taken care of that 1 over x. But this one here, that doesn't work. Okay, so we have to see if we can apply integration by parts. So integration by parts, the most complicated parts that I can integrate, well, I can't really integrate that. That's not an integral I know. So I'm going to use this as my dv part. So u is going to be log x. dv is equal to 1 over x squared dx. Okay, now it is important to bear in mind that you may choose the wrong dv to start, and you may want to try some other option. Okay, so that's something that you might have to consider if it doesn't work the first time. If you get integrals that don't seem to be going anywhere, you may want to reconsider what your initial choice was. So here I'm going to differentiate again. I'm going to differentiate this to get my du. I'm going to integrate this to get my v. I'm going to plug it into my formula, so I get negative log x over x minus, it's going to be v du, so it's going to be negative negative, so that's going to be plus, and 1 over x times 1 over x dx, or 1 over x squared. So I get negative log x, okay, over x plus the integral of 1 over x squared dx. Okay, so I've already integrated that one, so we know that becomes negative 1 over, that's going to be the integral of, that's going to be, it's going to be negative 1 over x plus c. Okay, so there's our antiderivative function for that, or starting function there.